Okay, let's jump right into this explainer and make the fundamental physics of electrical circuits absolutely crystal clear. Today, we're taking a close look at the exact mechanics of resistance, and we'll break down the critical differences between series and parallel circuits.
But before we start mapping out complex circuits, we kind of have to ask ourselves a basic but completely essential question. What fundamentally slows down or controls electrical current as it moves? We all know electricity is the flow of electrons, but they don't just shoot freely through a material without getting a little pushback.
To understand that pushback, we're going to follow a quick roadmap. 1. The anatomy of resistance. 2. Deriving the resistivity formula. 3. Series circuits, single pathway. 4. Parallel circuits, multiple paths. And 5. Real-world circuit calculations. Let's get to it. Starting off with Section 1, the anatomy of resistance. According to our sources, electrical resistance isn't just some random number. It's actually strictly governed by 4 key physical factors of the conductor itself. First up, you've got the material, because, some metals are just naturally better conductors than others. Second is the length of the wire. Third is its cross-sectional area, which is basically how thick it is. And finally, the temperature of the conductor. Those 4 pillars dictate exactly how much resistance those electrons are gonna face. Moving right along to Section 2, deriving the resistivity formula. Now, what's really cool about this part is how we can translate those physical factors into a precise mathematical equation. Let's walk through this step by step. In step 1, resistance, or R, is directly proportional to length, L. Think of it like walking down a crowded hallway, right? The longer the hallway, the more resistance you face. Step 2, R is inversely proportional to cross-sectional area, A. A wider hallway, way easier to get through. In step 3, we just combine them, so R is proportional to L over A. Now, to make it an exact equation, we add a constant of proportionality, the Greek letter rho. That gives us our famous formula, R equals rho times L over A. So what is rho? Well, that stands for electrical resistivity. This is a fundamental property uniquely tied to the material itself, like whether it's copper, nichrome, or tungsten. It measures how strongly the material resists current. And the absolutely crucial takeaway here is that resistivity is completely independent of the material's shape or size. The source data gives us a brilliant comparison that shows this exact concept in action. Take 2 copper wires. Wire X has a standard length and radius. Wire Y doubles the length, but it also doubles the radius. Because area is based on the radius squared, the cross-sectional area of wire Y actually becomes 4 times larger. So if you have 2 times the length divided by 4 times the area, the overall resistance drops by half. But check out the resistivity column. Rho stays exactly the same for both wires, simply because they're both made of copper. Okay, Section 3. Series circuits, single pathway. So now that we know what resistance is on a micro level, let's look at what happens when we string multiple resistors together in a single path. Think of a series circuit like a single-lane road. Connecting resistors end to end increases the overall effective length of the resistance. Because of this, the total resistance goes up. You literally just calculate it by adding R1 plus R2. As a result of this single-lane bottleneck, the total current flowing through the circuit drops, and the voltage gets shared across all the different resistors. Looking at these authentic study notes from our sources, you can easily see this principle applied. We have a 5 ohm and a 10 ohm resistor connected in series. To find the total resistance, you just add them together for a total of 15 ohms. Simple as that. And using Ohm's law with the 1.5 volt battery we have here, you just divide 1.5 by 15, meaning this specific circuit permits just 0.1 amps of current to flow. Section 4, parallel circuits, multiple paths. The big question now is, what if we want to add more pathways for the electrons to flow? Kind of like adding extra lanes to that highway? Well, in a parallel circuit, we open up multiple pathways. Because the electrons now have choices of where to go, the total resistance of the circuit actually decreases. This means the overall current drawn from the battery goes up. Plus, every single branch gets the full identical voltage. And practically speaking, each branch can be switched on and off completely independently. Now, calculating this decreased resistance looks a little different than it does in a series circuit. We use a formula where 1 over the total parallel resistance equals 1 over R1 plus 1 over R2. We have a great hand-drawn calculation from the sources to show this. Here, we've got a 1 ohm and a 2 ohm resistor in parallel. So we get 1 over 1 plus 1 over 2, which equals 3 over 2. You just flip that fraction around, and your total resistance is just 2/3 of an ohm. Placing these concepts side by side really cements the difference for us. A series circuit restricts flow. It acts as one long bottleneck that increases resistance and reduces current.
Parallel connections, on the other hand, ease the flow. They open up multiple independent lanes, ensuring the same voltage everywhere, while dropping the total resistance and bumping up the current.
All right, Section 5, Real-World Circuit Calculations. Let's put all this knowledge to the test. Let's look at a real-world application from the sources that actually mixes both of these setups together. Here we have a circuit schematic starting with a 6-volt battery. The current flows out and then splits into two 6-ohm resistors that are arranged in parallel. After those parallel branches merge back together, they connect in series to a 2-ohm resistor before finally returning to the battery. Let's break down the math for this. Step 1, you always want to solve the parallel section first. 1/6 plus 1/6 gives us 2/6. Flip it, and the equivalent resistance of that parallel block is 3 ohms. Step 2, we take that 3 ohms and add it to our 2 ohm series resistor. 3 plus 2 gives us a total circuit resistance of 5 ohms. Finally, step 3, we plug this into Ohm's law. Current equals voltage divided by resistance, so 6 volts divided by 5 ohms gives us a total circuit current of 1.2 amps. Which brings us to our final thought for today. Based on everything we've just covered about multiple pathways, voltage, and total current, do you think the lights in your home are wired in series or in parallel? Well, since turning off one light switch in your kitchen doesn't plunge your entire house into total darkness, you now have the exact physics knowledge to answer this. They have independent pathways, so they absolutely must be wired in parallel. Next time you flip a switch, think about the circuits around you. You now have the fundamental concepts to decode exactly how they work.